record this. All right. So last day we got through to, I think, page 6 of the notes, right? We went through this typed up example, and then we were about to start this next example that we're going to do together. So we'll use that as our review of last day, right? And then we can go in and talk about confidence intervals for one sample mean, sigma unknown. And then today we'll start talking about another type of data or another type of question, which is paired data or matched pairs. So that's where we're headed today. Let me add a page here. So, zoom in so we can read it. So what we're going to do is, so in chapter 4, we introduced the first type of problem, which was one sample mean sigma known, where we're pretending to know the population standard deviation. But now for most of these questions, the standard deviation is going to come from the sample rather than the population. Okay, so, and that's what we talked about last day. We also talked about, okay, well, we need to use the t distribution instead of the z, and also how do we use the t table to find our p-value, but also our critical value for our confidence interval. Okay. Oh, and I'm giving you assignment 5. After today, you'll be able to do all except for one of the questions. So you'll have to wait till next day to be able to do all of them, but that's pretty good. And so at least you can get started on it because it is a little bit longer, right? And then it's due on the same day as the test. It's basically another practice test, right? And so it's kind of what you can expect, or the types of questions that you can expect on a test. It's platypus themed. I used to have a platypus test, but all my tests then evolved to animals that start with M, and so platypus was out. And fun fact, plural of platypus is platypuses. Cute. So here's a boring example. No, not really. Summit Projects is a full-service interactive agency that offers companies a variety of website services. Great. Summit recently redesigned a client company's website and wants to show that sales have increased. Of course, that sounds like a good idea. Before the redesign, the average sales were $24.85. Okay, so before the redesign, that was the mean. After the redesign, an analyst selects 58 sales, right? So a sample size of 58 sales records at random from the client's 2,000 access logs. This 2,000 doesn't actually factor into anything. It's just, that's how many they have. And she, I like the she in there. And she finds a mean amount. I didn't put that in there, but I like it. Spent of 2605. Okay, so that's your sample mean now. And a standard deviation of 1020. The way that we've got this question, it's implied that this standard deviation came from the sample. And that's where my mess up with assignment 4 was, because that standard deviation was actually from the sample, but I was hoping no one would notice. Also, we hadn't covered that yet, so I felt pretty safe. But that was my screw up. So I'll fix that question and show you guys what it should have said to make it sigma known. But I'll do that later. It'll be in the solutions. Is there evidence the mean sales have increased since the redesign? Fair enough. Okay. Here's our sample mean. Right? So same situation, we have a sample mean that we want to compare to some value. That value has to be the 2485, right? Is that larger, significantly larger than 2485? So 2605 is greater than 2485. We want to know if it's significantly greater than 2485. Okay. So here we go. I'll start down here. Example 2. Whenever it says, is there evidence of something, you have to do a full hypothesis test. Right? And so step 1 is to state your hypotheses. Of course, you don't have to outline the steps, but I do just to show you that they're always the same. The null hypothesis for one sample mean, whether sigma is known or unknown, it's the same, right? And so we talk about, okay, well, is mu equal to, and the value we want to compare our sample to is 2485. Just going back here. This is our hypothesized mean. N is 58. X bar is 2605. X bar is the mean from the sample, right? So that's how you know. And standard deviation from the sample, therefore, sigma is unknown. And so S is 1020. We want to know if the sales have increased, which in terms of mu to 2485, that would be mu would be greater than 2485. We only care if the sales have increased, right? And so we don't care if they've decreased, so we only care about one side. So it's a one-sided test. One-sided test. I make a note of that here because later on in step 3, that's when I need it, right? So we kind of parking lot it for a little bit, but it's good to make a note of if you have a one-sided or a two-sided test just for later. Okay. So there's your null and alternative hypotheses. Great. And so now we're ready to go on to step 2. Step 2 is do the test, or do the do, as I like to call it. T, because we said sigma is unknown, right? We can't calculate a Z anymore, so we're going to calculate a T. T is X bar minus mu over S over root N. X bar is the 2605. Oops, 2605 minus 2485. Divided by 1020. Divided by the square root of, what was our sample size? 58. In this calculation, right, we're just seeing how far is 2605 from 2485, taking into account the standard error. And so I'll write out the steps just so you can check your calculations. But as long as you've shown me all the values plugged in where they should be, then you can skip right to your answer if you want to, just because sometimes it's easier to just do it all in your calculator right away. Right? Or if you want to break it up and show steps like I do, that's fine too.
2605 minus 2485, 1.2 divided by, and then 1020 divided by square root of 58, 1.339325615. Remember, you're not going to round any values until the very end, right? So you have to keep all your decimals until the very end. 1.2 divided by that is 0.895973307. T, it's not something you have to memorize, but T, you have to have at least 3 decimal places, right? You can have more than 3, whereas Z, you had to have 2 decimal places exactly in order to use the Z table, right? And so for T, again, we're trying to match the table. The table has 3 decimal places for T, and so that's how you'll know. And so we have 0.896 to 3 decimal places. Good. Already, we suspect that this is not looking good for the consultant who did the redesign, right? Just because this is not that many standard deviations above 2485, right? If he was successful in significantly increasing the sales, right, this T would be bigger than 2, typically, right? And so just as a quick check-in point, with a T this low, right, we already suspect that we're not going to reject the null hypothesis, right? Because if T is large enough, then you can reject the null hypothesis, right? So already we kind of know where this is going. We just have to go through the motions. So now in step 3, you're going to find the p-value. So step 3 is find the p-value. So what are we going to do? You can just have a look here. And remember, you've calculated a T, and so of course you have to use the T table. And to use the T table, you need to know your degrees of freedom, which for one sample is just your sample size minus 1. And so in our answer, we have to jot all that down, right? Just tell me where you're getting stuff from. So using the T table, with degrees of freedom equal to n minus 1, just showing off that you know how to find the degrees of freedom, which is, what was it, 58? 58 minus 1, which is 57. However, when you go to find 57 on here, we're kind of stuck, right? So we've got options, we've got 50 or 60. And what we said last day was that it's really important that we go to 50, right? Even though we're closer to 60, but a degrees of freedom of 60 is saying you have a sample size of 61 when you actually only have 58, right? So that would be bad, right? And so we always have to round down if our degrees of freedom aren't on the table, right? And so we're going to be using 50 degrees of freedom. So I'm going to write that down in my notes. Because when I'm marking your stuff, you should probably tell me that, oh, these were my degrees of freedom, but in the table, I'm going to be using 50. So, but using degrees of freedom equal to 50, okay, we find at another page. Okay. And here's where the setup is going to be the same. So for all of the types of problems, the 3 types of problems from chapter 5, we're going to be calculating T's. And so finding the p-value is going to be the same for all of these, right? And so what you do is in the middle of your page, you write out your calculated t from step 2 in absolute values, symbols or brackets, I guess. So you say t is 0.896, and then these vertical lines are saying absolute value, because remember the t table only has positive values. So if you found a negative value of t, the absolute value symbol just says get rid of the negative, right? And so we take the positive version of our t and we try to place it, figure out where it would go on our lines of degrees of freedom, right? So 0.896, trying to place it here. Right? But I just imagine grabbing it from step 2 and I just hold it and I just take it. And so I've got 50 degrees of freedom and I go until I find, and I don't have to go very far in this case, I find that it's somewhere between 0.849 and 1.047. Right? So my calculated t is somewhere between these two values. Right? And so that's what I'm going to write here. Thought I'd have to. Was it 0.847? Thank you. And what was the other one? Thank you. Okay. I'm always going to do just the less than signs. Okay. So it's good to just get in the habit of doing something consistently, even if you don't like inequalities. I don't even like inequalities, but it's the only way to show this. This would be a huge sentence if you had to write it out, right? So we don't even bother. So also in the center of the page and wrapped up in less than signs, we're going to find our one-sided p-value is going to be between two values. Notice that I just keep the same signs, right? And here, this is where you refer to your alternative hypothesis. If you had to find a two-sided p-value, of course, you would write two-sided. Okay. But what we're going to find is that here, so 50 degrees of freedom, we found our calculated t is somewhere between these two values. So then what we do is we just trace down to the one-sided p line. And it's just saying that our one-sided p is somewhere between 0.15 and 0.2. It's really important that we read it from right to left, right? Because the p-values are actually decreasing as we move further and further out into the tail, right? So when we write it out, the only switcheroo that we have to make is that our p-value is between 0.15 and 0.2. Right? But that's the only kind of switch that we're making. That's the end of my pen. So then our one-sided p-values between 0.15 and 0.20. It's a little unsatisfying to just have a range for our p-value, but of course R would be able to give us a more precise p-value. But also, this gives us the information that we need, right? Because if we know that it's somewhere between 0.15 and 0.2, well, both of those are higher than the alpha level of 0.05, right? Which, again, we don't have enough evidence to reject H0 because it's not smaller than the alpha level, right? So now in step 4, it's time for our conclusion. Your conclusion is always going to have 3 pieces, right? And so first part is we have to compare our p-value to our alpha level. I didn't tell you what alpha level to use, so the default is 0.05. Okay? So what we say is, since our one-sided p-value is between 0.15 and 0.20, it is not less than our assumed alpha level of 0.05. Oops, comma. If our p-value is not less than the alpha level, right, that means we don't have enough evidence to reject H0. Right? It means we haven't moved far enough into the tail to be able to say that they're significantly different. Right, so what we say, which means, and this is the second part of our conclusion, which means we do not have enough evidence to reject H0. It's kind of bad news for summit projects, right? Because what does that mean in terms of the question? Well, it means the question was, is there evidence the mean sales have increased since the redesign? No, there isn't, right? And so we just reword the question as an answer. There is no evidence that the mean sales have increased since the redesign. Therefore, there is no evidence that the mean sales have increased since the redesign. Probably not what they were hoping for, but nothing we can do about it. Okay. Any questions about that one? Okay. So, I've just scrolled down a lot. I don't know if everyone can fill it in later. So then let's move on to confidence intervals. We've already seen confidence intervals when we know sigma, right? That was on assignment 4. And so now we're moving to, okay, well, what does the confidence interval look like when we don't know sigma? Well, we just replace sigma with a sample standard deviation. And instead of a z star, now we're calculating a t star. And what we said last day was to find t star, right? We have to remember for sigma known, we used z star, right? And so what we said was, if we wanted a z star for, say, a 95% confidence interval, then we go from 95 and we just scroll all the way down to 1.96. Now, what we're going to do is, instead of going all the way down to the z star line, you just go until you hit your degrees of freedom, right? So your degrees of freedom are playing a part in your t star, but besides that, it's the exact same thing, right? Finding your t star versus your z star. So let us get back to the note. So our degrees of freedom, bless you, are still n-1, right? That's the same for hypothesis testing and confidence intervals for each question. X bar is the sample mean still. T star is the critical value, that's what we call it. And we find it using the t-table. Just like Z star, T star is the only thing that determines your confidence level, right? Nothing else is contributing to the confidence level. Everything else is from the sample, right? So if you want a 98% or a 95% or a 90% confidence interval, right, that's going to come from your critical value. S over root n is still called the standard error of x bar, and t star times s over root n is still called the margin of error. Any questions before the example? All right. Business bankruptcies in Canada, blah, blah, blah. Skipping that whole first paragraph. You can read it if you want, but a study is based on a random sample of 75 reports from the current year. The average debt, liabilities minus assets is $92,172 with a standard deviation of $111,538. 111,000. Squeeze 1,000 in there. Construct a 95% confidence interval for the average debt of these companies at the time of filing. And so here, the main thing that we're going to look at is, okay, of course we know the standard deviation. The question is, where did it come from? Here we're going to say, okay, well, we collected a sample and we found the sample mean to be this, and here, this is your standard deviation from the sample. Therefore, sigma is unknown. And we're given things like n is 75 and x bar is 92, 172. So first thing we have to do, and often if I'm doing these by hand myself, I write out the formula just to see what information I have, what information I still need to find, right? And then I can go ahead and fill it in once I have everything, right? But I'm always going to need to find T star, so you could just start there if you want to. Remember these boxes that I've made? Pretty proud of them. No, these boxes that I made are just highlighting everything that you need if you want full marks on the test or the assignment. So none of this is optional, okay? And so that's why I've made those boxes, because a lot of the time people think, well, surely not all of this is mandatory. It is actually. It's all mandatory, and so I've highlighted that using the box, right? And so whenever something's in a box, then you have to have all of that for full marks. Like I said, in your calculation, if you wanted to skip this little bit, that line, that's the only optional one. But the way things are coded in the background, that was a big hassle to break out. So just leave it in there. So what we're going to say, right, because we need, right, we're given x bar, we have s, and we have n. The only thing that we need is our t star. And so we have to explain how we're going to get it. So using the t table, again, with degrees of freedom equal to 74, but using 60. I guess this is a new problem. We didn't know that, but there it is. If you tried to go to the table, tried to find 74 degrees of freedom, you've got options between 60 and 80. Of course, we're going to round down to 60 again, just like before. And so we have to use 60 degrees of freedom, and I guess we can just do it. We wanted a 95% confidence interval, and so 95 going down to, oh, I just have it here, 2.000. Very nice. Critical value. Jibes with our 68, 95, 99.7 rule. Right. So it's all matching up. And so we've got but using 60 degrees of freedom, we find T star is 2.000 for a confidence level of 95%. now we can plug it in, right? So now we have all the components that we need to plug into this formula. The calculations themselves aren't that bad, right? Because we're multiplying and dividing here, the order doesn't matter, right? And so you're going to solve for the margin of error. Remember, the whole plus minus chunk is the margin of error. So you're going to solve for that. Show me what it is. Right, so that's mandatory. If you want to skip to here, that's fine. But I like to show it with all the decimals and then show that I've rounded properly. But as long as you round properly in the last step, then you're okay. I didn't tell you how many decimal places to use, but when we're talking about money, it's easy, right? Because we have to have 2 decimal places, right? And so then as soon as we're talking about money, then you know it's going to be 2 decimal places. All right. So we find our intervals between 66 and 117,000. And so now we have to interpret it, right? As soon as you've made a confidence interval, you have to interpret it. And we use that same blurb as before, right? So we're 95% confident that the interval from 66,000 to 117,000-ish captures the average debt of these companies at the time of filing. Notice that everything from here on out, right, captures, I'm just rewording the question as an answer because we were told to construct a 95% confidence interval for the average debt of these companies at the time of filing. And so here we're 95% confident that this interval is capturing the average debt of these companies at the time of filing, right? So you are often just able to steal that from the question and just plug it in. When you're listing your interval, just as a side note, I didn't see it too much on assignment 4, so that's good. You have to have your lowest one to your highest one, right? If you've got them reversed, I have to take some marks off. Yeah.
Will a confidence interval question always say confidence interval?
Yeah. Yeah. Because it'll be something. Yeah. There's no way around it. I'll always say construct a 90% confidence interval or construct a 95% confidence interval. And so, yeah, I'm trying to think. There's no other way to ask it. So it'll always ask you for a confidence interval. Cool. Any questions? Oh. Okay. We'll do this riveting example together. A manufacturer of high-resolution video terminals must control the tension of the mesh or on the mesh of fine wires that lies behind the surface of the viewing screen. Very important stuff. No, I have no idea. The tension is measured by an electrical device with output readings in millivolts. I don't really care about units, though, in general, right? Unless it's money, then I care. A random sample of 20 screens has a mean of 306.32 and a standard deviation of 36.21. So already we know that n is 20. This is our x bar, right? Our sample mean is 306.32. And this is our sample standard deviation is 36.21. Because this is our sample standard deviation, sigma is unknown. Give a 90% confidence interval for the true mean tension mu of all the video terminals produced this day. It's kind of redundant times 2. So is it redundant? I don't know. Or maybe that undoes the redundancy. Why am I saying that? Because the true mean is the population mean. Mu is also the population mean, but also of all the video terminals is also the population mean, right? So I've mentioned the population mean 3 times here, or I guess they have, I stole it, but I've always stolen them. Unless they're about animals, then I didn't steal them. Then I made them up. Okay. So we want to make a 90% confidence interval, right? And so what I always end up doing when I do a confidence interval is I end up writing out my formula first. Things got small. X bar plus minus T star times S over root N. Kind of an extra step, but for me, it's nice to have a look at all the things that I need. Right? This is when I'll notice that I need a T star, right? And so that's going to prompt me to go to the T table, of course. So what we can say is using the T table, with degrees of freedom equal to n minus 1, which is 20 minus 1, which is 19. If we go to our T table and we look for 19 is actually on here, right? And so we can use it. And we want to make a 90% confidence interval, right? And so we go to 90 here, and then we stop at 19 degrees of freedom. So we get a T star of 1.729. I think, unless I went cross-eyed. I think, okay. So 1.729. Using the T table with 19 degrees of freedom, we find T star is 1.729. So, yeah. Short-term memory is gone. And then I'll throw in for a 90% confidence level. Right, just to emphasize that, or more to remind myself that I'm doing a 90% confidence interval. Now, I'm ready to plug in my values. So now I can actually write out my formula. X bar plus minus T star times S over root N. I can plug in my values. X bar was 306.32 plus minus T star, which is 1.729 times S, which is 3621 over the square root of 20. Guess I better just add a page here. I'll show my work, but as long as you show all the values plugged in and then the margin of error before you find your interval, then you're safe. So 3621 divided by the square root of 20, I get 8.096802147 times 1.729. And then 306.32 just stays out there for a bit. So then I'm going to multiply that by 1.729. And I get plus minus 13.999379091. That's my margin of error, right? And so if you wanted to go from here to here, that's fine, right? But I do want to see what your margin of error is. So 306.32 plus minus 13.9999. course, I'm going to store that so I don't have to type it in again. To write out our confidence interval properly, right, we put them in round brackets, we calculate our lower bound first and then our upper bound, right? And so because I've stored my margin of error, I can do 306.32 minus that guy, 292.3206291, separated by a comma, and then 306.32 plus my margin of error, 320.3193.709. Or if we're going to round it, even though I didn't tell you how many decimal places to use, right, and it's not money, so it's not obvious, but because in the question, I only gave you 2 decimal places here, right, you can just give me 2 decimal places back, right? So you don't have to go more than that, but you shouldn't go less than 2 either, right? You should always kind of match whatever I'm doing. So to 2 decimal places here, we get 292.32 up to 320.32. Again, once we've made a confidence interval, we have to interpret it, right? And so we use that same sentence structure. So we are 90% confident the interval from 292.32 to 320.32 captures, and then this is where we just sneak in whatever I want to do to make a confidence interval of, captures the true mean tension mu of all the video terminals produced this day. Captures the true mean tension mu of all video terminals produced this day. Nice. Any questions about that one? No? Pretty good. So really similar to what we were doing in chapter 4, right? And in fact, even in the next section, things just stay the same. It's just one little thing is changing. I see some people writing still, so I don't want to scroll, but I'll give the little preview, I guess. So far we've been talking about one sample, right? So we've collected one sample and we have one sample size and we found the mean and the standard deviation of that one sample, right? A lot of the time, we're not just gonna have one sample. How does it compare to this one value, right? Often we'll wanna have 2 samples and compare the 2, right? And so there's 2 main ways that we can collect 2 samples. The first one is if these 2 samples are paired on one individual, right? So in other words, if we've made 2 observations on the same individual, then we have paired data. And then in the last section of chapter 5, we're going to talk about, well, what happens if we just have 2 independent samples that we want to compare. Right. So from here, oh, I guess I can just scroll down, or I just need to scroll down. From here, we pick up the pace a little bit, just because now you're more familiar with hypothesis testing and confidence intervals. We're more familiar with the t-table, and what you'll find is we'll just calculate t's for all of these. It's just the calculation is going to change a little bit. But then once we have a t, we use the t-table the same way, right? And so now very little is going to change from each type of question. And so paired samples or paired data, matched pairs, I use them all interchangeably, but they all have the word pair in them. And so I think the most helpful blurb is the one I put on the side, right? If we've made 2 observations on the same individual, or sometimes if we've made 1 observation on each of 2 similar individuals, kind of also the case, we have paired data. So whenever there's a way to naturally say that, oh, of course, this observation from this column goes with this observation in this column, then you have paired data. Right? All of these are versions of the same thing. So pre and post data, before and after studies, right? So let's say you're hosting a running group, just for kicks, I don't know. I'm not a runner, so I don't know, but and you want to show that after someone's attended your running group, they are significantly faster, if that's the goal, than they were when they started, right? So then you have before and after data. So what you would do is you would get a sample of someone's before running times, right? Or your group's running times before you start. So the very first day of your running group or whatever. And then at the end of your training, you do the same thing, right? You do the test and you figure out what your running time was after all this training, right? And so now those 2 observations are linked to the same individual, right? And so what we do is we analyze the differences between these 2 groups, right? Or these 2 samples. And the reason for that is because if you have a really fast person, you know, they started really fast, so their initial time is really fast, even if they've I guess, decrease their time, right? If they've become faster, right? There's improvement within that person. Right? And so, and even someone who starts off really slow might improve, but in the end, maybe they're still a really slow runner, right? But for them, they've improved, right? And so to capture that change within each individual or within each observation, we calculate the differences in a new column. Or for us, right, you've written test 1, you got a grade on test 1, and you're gonna write test 2, you'll get a grade on test 2. And so what we can do is we can analyze, well, overall as a group, did we improve our grades from test 1 to test 2? And so those would be paired data, right? Because I can link your test 1 grade and your test 2 grade to you, right? 2 observations on the same individual, right? So that's when we know we have paired data. And so probably the hardest part is figuring out when you have paired data. But then once you've decided that you have paired data, then what we do is we just analyze the differences as if they were 1 sample, right? So now what you do, you have your test 1 scores and your test 2 scores, for example. I make a new column of the differences for everyone, right? So the change. And then I calculate the mean and the standard deviation of those differences, and I analyze those as if they were just 1 sample, right? Because those differences capture what happened to each individual. Okay? And so that's all in here. As long as you subtract in a consistent order, I always subtract my first column minus the second column, just because that's how I read it. right? But if you wanted to do the other way, that's fine. As long as you're consistent, it actually doesn't matter. Then all you have to do is find the differences. I've got these little notes about assumptions. If the assumptions for applying the t distributions are met, then we use one sample t procedures to perform inference about the mean difference mu subscript d, right? So now, because we're talking paired data and we've boiled it down to this one sample of differences, we indicate that with a little subscript d or subscript diff. But that's really the only difference. So, what changes? Oh, any questions before I ramble on? Great. So, what changes in terms of our hypothesis testing, we'll start there, is, well, once you've decided you have paired data, then what's really, really nice is that this exactly will always be your null hypothesis. Right? So once you've decided you have paired data, you don't have to pick a value, right? Because we're always going to assume that sample 1 is the same as sample 2. If two values are the same, then the difference will be 0. Right? And so we always have to assume that the mean of the differences is 0 until we have proof otherwise. And so the only thing that's going to change is the sign in the alternative hypothesis, depending on the question, right? Same as before. But so it's a little bit easier almost than one sample mean, just because you already know that you're comparing the mean of the differences to 0. In our test, our t calculation, then we've got, all I've done is just put little subscript d's everywhere to indicate that, hey, here's the sample mean of the differences minus the hypothesized mean of the differences. Remember, the testing, we always assume the null hypothesis is true. The null hypothesis says that mu d is 0. And so that's why I've got this second t down here, where I've actually just eliminated mu d because it's 0 always. And so you can just ignore it over the standard deviation of the differences over the square root of the number of the differences. The number of differences is going to be the same as the number of individuals, right? Because even though you have two samples here, right, there's only going to be the number of individuals differences. Okay? So that's what your ND is going to be. And for your degrees of freedom, you have the number of differences minus 1. Okay? So exact same setup as before, right? With our one sample mean, it's just this special case where we're analyzing the differences, one sample of the differences. Once we have our p-value, our conclusion remains the same, right? Our p-value still has to be small enough, right? Smaller than the alpha level to reject H naught, but then we can go from there. Any questions? Okay. So example 5. This is a bit of a longer one. It's one where I've typed out the solutions, and so we're just going to talk about them. Some of these are just in there just to show you a little bit extra, right? Really, part D is the moneymaker, right? So we'll just kind of talk about parts A, B, C, and then part D is the actual hypothesis test that we'll do. And then part E is just kind of making the connection between hypothesis testing and confidence intervals. So 200 observations were randomly sampled from a survey called High School and Beyond. Sounds intriguing. The same students took a reading and writing test and their scores are shown over here. It didn't really contribute, so I just put them on the side. Okay. And so we've got 200 students, right? Each, of course, has a student ID. These two columns don't actually contribute anything. It's just showing that, well, this is the same individual that got a reading score and a writing score, right? And so that's a hint that we have this paired data. Right? And so each individual took a reading score and had a writing score, and we're going to analyze to see if there's a difference between these. Okay. And so what we're going to be doing is we're going to calculate, or not us by hand, of course, but we would calculate a column of differences. Right. So we decide that this is paired data just because we've made 2 observations on the same individual. Okay. So for part A, oh, I guess I don't have to write it down because I've got it in the box. This data is paired since we've made 2 observations on each student. Therefore, the reading and writing scores of each student is not independent of each other, right? It depends on the student, right? Are they strong in reading and writing? Usually, typically, I think we can all agree that those kind of go hand in hand, right? Weird circumstances, but typically reading and writing are kind of linked, right? And so if it's the same student writing these tests, right, those should be paired. I've also got the R code for you here. If you wanted to do it on the side, it's definitely not something I'm expecting, but just to show you, you do have to install the Open Intro package, which you know how to do now, and then use the Open Intro library, of course, and then you can bring in this HSV2 data. Since I was doing it anyways, I figured I'd show you the code. Oh. So are the reading and writing scores of each student independent of each other? No, they're not, right? Because we've made 2 observations on the same individual. Part B, kind of a extra piece. Compare the distributions of the 2 groups. At first glance, does there appear to be a difference between the average reading and writing scores? Okay. So what I did was, well, I said, because I've got a numerical variable, right, the scores are all numerical, right, and then I've got a categorical variable, the reading and the writing, I actually had to restructure the data because we've made side-by-side box plots in the lab, right? And so to make side-by-side box plots, we have to have a column of numerical and a column of categorical. And so I just had to make those, right? Not something I would expect you to do again, but, and then I just made the box plot. But it's there in case you want to try it. Okay. And so looking at these, and a lot of you had something similar in the lab, right, where you're trying to discuss something like this and, well, they look similar, right? Because there's a lot of overlap here. The one thing that we could say is that maybe the maximum of the reading scores goes a little bit higher than the maximum of the writing scores. But besides that, there's nothing really interesting going on here, right? And so already we suspect that there is no difference between these 2 groups. No significant difference between these 2 groups. Are the assumptions for inference satisfied? What we do in reality is we just calculate the variable, or if we have it already, we make a histogram of it. But in this case, we want to calculate the differences, which is just, I'm going to do the reading minus the writing score. And then I make a histogram of it over on the side. And sure enough, it looks approximately normal. And so then I can say, well, then my assumptions for inference are satisfied because I have a large sample size. I have a sample size of 200. And the distribution of the differences looks approximately normal. again, assumptions for me for t-tests, I'm not going to test those so much. It's going to be when we get into proportions, then it'll be important, so then I'll emphasize it more. Here I've included it just for fun, but so for assumptions for chapter 5, not so much. Oh yeah. D. Do these data provide convincing evidence of a difference between the scores on the 2 exams? Right. So now we want to know if there's a difference between these 2 scores, right? We're not asking if one is higher than the other, right? So here, this is where we get that we have a 2-sided test, right? And so when you see something, is there evidence of a difference? It gets tricky because we're analyzing the differences, right? But here, what I'm asking, the difference between the 2 scores. And so that's what makes this a 2-sided test. Like we said, we have to now calculate the mean, the sample mean of the differences and the sample standard deviation of the differences. Right? I just use R to do it. And now we can go ahead and do our hypothesis test, right? Now that we have our sample information. And so, I should put down here that the number of differences is 200, because we had 200 students write each of the tests. Like I said, if you have paired data, then this is your null hypothesis, right? Nothing has to change. But you do have to have mu subscript D to tell me that you know that you're analyzing the differences. Equals 0. How does the difference compare to 0? And then we have a 2-sided test because, right, we want to know if there's just a difference between these 2 groups. Right, and so here I'll say this is a 2-sided test. Now, keeping in mind that we're just using the t with the sample information of the differences in here, we can plug in these values and we calculate a t of negative 0.867. Again, doesn't look good, but it also confirms what we saw in that side-by-side box plot, that there's really probably not a significant difference between the 2 groups, right? Because this is, again, not that far away from, well, a difference of negative 0.545 is only 0.867 standard errors below 0, right, is what it's saying. So our t, our calculated t, is negative 0.867. So now it's time to find the p-value. Once you have a t, you know what to do. You have to go to the t table. You have to find your degrees of freedom. You have to place your t somewhere along this line. We have 200 minus 1, so 199 degrees of freedom. But then once you go to your table, you're going to find that you have to choose between 199 is between 100 and 1,000. We have to go to 100. Right, and so now you take the absolute value of 0.867, so you drop the negative, and you try to figure out where it goes on this line. It goes between 0.845 and 1.042. Funny, these examples turned out to be very similar. It's okay. So you jot those down. Right? You start by writing out your calculated t in absolute value brackets, and then it's between these two values from the table, and then our two-sided p-value, now that we can scroll down to the bottom of the table. Degrees of freedom, so we're somewhere between here and here. And then we scroll down to our two-sided p-value. Our two-sided p-value is somewhere between 0.3 and 0.4. So you can jot those down. Remembering to list them from right to left, right? Smallest to largest. Just gonna throw the definition of the p-value back in your faces, right? So the p-value is the probability of seeing something as extreme or more extreme, and that's why we're always looking in the tails, as something that you saw, assuming that the null hypothesis is true. And so here, the p-value is the probability of obtaining a random sample of 200 students where the average difference between the reading scores is at least 0.54, if in fact the true average difference between the score is 0. That probability is pretty high, right? And so that's why we're not going to reject the null hypothesis. But I just wanted to throw that in there, just because. Our conclusion, since our two-sided p-value is between 0.3 and 0.4, we don't know exactly where in there it is, but we know it's somewhere in there. It's not less than our assumed alpha level of 0.05, which means we do not have enough evidence to reject H naught. In terms of the question, right, I'm just going to reword the question as an answer. This means these data do not provide convincing evidence of a difference between the scores on the two exams. Right? So, your conclusion always has those three parts. What do I have over here? Oh, yeah. And the last part. So we're not going to make the confidence interval, although you totally can if you want to. Suppose we were to construct a 95% confidence interval for the average difference between the reading and writing scores. Would you expect this interval to include 0? Right? And so here we're kind of reverse engineering, because all we know is based off of our data, we didn't have enough evidence to reject H naught. Right? And so we can use confidence intervals, right, and say, well, if our hypothesized value is inside this interval, then you don't have enough evidence to reject H naught. Whereas if the entire interval is off of the hypothesized value, then you have enough evidence to reject H naught. Right, now I'm just asking you to think about it in reverse. Well, if we don't have enough evidence to reject H naught, which says that the mean is 0, then that means that 0 must be in the confidence interval, right? Just because of the link. And I'll show you. So if we were to construct a 95% confidence interval for the average difference between the reading and writing scores, we would expect this interval to include 0, as our two-sided hypothesis test at the alpha equals 0.05 level concluded the population mean was not significantly different from 0. And I'll show you the output that we get in R. So in lab 6, which got bumped to the second to last lab, just because I'm pretty sure we're ahead of all the other classes. No, that's you guys. That's not me, that's you guys. Bragging rights for me though. No, so we're a little bit ahead of everyone else. And we're just starting these t-tests. And so we had to kind of rework the labs and reorder them. But talk about that in the lab. So the t.test command takes, so we already saw it for one sample, and you can take one sample and then the second sample, and as long as you specify that parent equals true, then it'll say gotcha. What I have to do is find the differences and analyze the differences. And so the parent equals true is what makes it a paired t-test. And it'll just confirm that in the output, but it'll calculate your t, it'll give you your degrees of freedom, and it'll also give you your p-value. We said our p, all we know is the p-value is somewhere between 0.3 and 0.4. Sure enough, 0.3868 is somewhere between 0.3 and 0.4. And then what's nice about having a two-sided test, notice that I didn't specify the alternative, and that's just because the default is a two-sided test. So I don't need to say that. If you do a two-sided test, it also gives you your confidence interval. Notice that your confidence interval for the differences, the mean of the differences, goes from a negative to a positive, so 0 must be in there. So that's just confirmed that 0 is in there. Cool. Am I expecting you to do any R code or read any R code on the test? No, absolutely not. I'm just throwing it in there more to help you out in the lab when you get there, because then you've seen it at least once and in context of these things that we're doing by hand. Okay. Any questions about that one? Okay. Time flies when you're having fun. Hi, guys. How about this? How about this? Over the weekend, try this one on your own. Just try it. And then we'll go through it when we meet on Monday. How about that? How about them apples? If you don't have assignment 5, you should grab one. If you didn't get your assignment 4 back, you should grab it.